So that's one complication. So we can start looking at the temperature gradient field and see how it evolves in time. So this shows the TDR, the radial temperature gradient, in degrees Celsius per kilometer for the two different times. And the RMW on each plot is in magenta. So we have a warm core, which means in this region the radial temperature gradient is negative. So this is, we have our warmest air near the center, and you have the largest gradient just inside the eyewall. One thing to notice here is the height where the radial gradient is greatest is not the height where the perturbation temperature is greatest. So they're not, in general, they're not related to each other in any direct sense, because the perturbation temperature is the integrated effect of this gradient. So you can't just look at where the warm core is maximized and guess where the gradient is strongest. But we see when we go from the left plot to the right plot, as the storm weakens in terms of wind speed, and the temperature field changes, we get a substantial weakening of the peak radial temperature gradient. But what we want to look at here is the change in the radial temperature gradient, because we're trying to understand how the temperature field relates to the wind field. So we want to see how the change in the temperature field relates to the change in the wind field. So this plot here on the left is the 24-hour change in the radial temperature gradient. So the difference between this plot and that plot. And so inside the eyewall, or inwards of the eyewall in the region of strong gradient, you get a positive change in the radial temperature gradient, which means a weakening of the radial temperature gradient. So it's a decreasing magnitude of the negative radial temperature gradient. And just to demonstrate that the approximate form of thermal wind balance that I'm using is valid, on the right is the 24-hour change in Vg times dVg dz. So if we go back, that's this term here, R doesn't change in time, and these are constants, so all we care about is how the Vg dVg dz, how that change compares to the change in dTdr. Because if this works, if this is a correct formulation, then they should be very similar. And they are very similar. There's close correspondence here. So this shows that this formulation is an accurate approximation to thermal wind balance. I want to make clear that this is not an evaluation of whether the flow itself is balanced. It's just a statement that the gradient wind, that the shear of the square of the gradient wind is well related to the radial temperature gradient, which is just a statement of the definition of thermal wind balance. But we actually have large imbalance in the boundary layer, because I'm evaluating the gradient wind here, not the actual tangential wind. So these are the, let me make sure I'm doing this right. So these are the same figures here, but so the point I want to make is that this weakened temperature gradient, so the temperature gradient is negative, but a weakening of that means a positive change, which is this yellow region here. That corresponds to a decrease in the magnitude of the vertical gradient of the squared gradient wind, which is this positive change. And so the gradient wind, if we go back to the wind field, the wind is decreasing with height. and the gradient wind is also decreasing with height. So that's a negative term. And so a decrease in the magnitude of that shear is a positive change. And so this is really saying that the changes in the temperature gradient are related to the changes in the shear of the squared gradient wind. And if this is very confusing, that's kind of the point of this. This is very difficult to interpret. It's hard to think about this as relating to the intensity of the storm or the structure of the wind field itself. It's a little bit easier to think in terms of just the gradient or the vertical shear of the gradient wind, dVGdZ. And now this is no longer precisely correspond. This doesn't actually relate through thermal wind balance directly. Now we're neglecting the other term, multiplying dVGdZ. But in this case, it's still in the mid-troposphere, corresponds spatially relatively well with dTdr. So in this case, in this simulation, the change in the radial temperature gradient corresponds relatively well to the vertical gradient and the gradient wind speed itself. But no, this is still kind of complicated, and there's a lot of spatial variation here that makes it difficult to interpret. So now if we look back again to the 24-hour change in temperature, and now what I'm showing you on the right is not the 24-hour change in the tangential wind, but the 24-hour change in the gradient wind. So over this period, when the storm is weakening, the gradient wind speed decreases generally through the depth of the eyewall. But the weakened temperature gradient, which is associated with this cooling of the mid-level eye and somewhat warming of the eyewall, so that this pattern is a weakening of the temperature gradient. As I just showed you, what that's associated with is the vertical gradient of the gradient wind. And so it's not the fact that the gradient wind is weakening that's associated with the weakening of the radial temperature gradient. It's a change in the vertical gradient of the gradient wind. And so what this actually means is that this weakened temperature gradient and the cooling of the mid-level eye, that corresponds with the fact that the gradient wind weakens less at mid-levels than it weakens at low levels. So the strongest weakening, the strongest spin down of the storm is at low levels. And because you have spin down at mid-levels, but it's weaker than the spin down at low levels, and that means, and that's associated through thermal wind balance with these temperature gradient changes. So we can't interpret the changes in the temperature field as directly relating to the weakening or strengthening of the storm itself, but rather more complicated derivatives of that change and the vertical structure of that change. And then finally, the greatest weakening of the tangential wind is in the boundary layer. So this is the 24-hour change in the tangential wind, and it's in the boundary layer. It's a much greater spin down, and it's concentrated there. That's the strongest weakening of the storm. But this boundary layer maximum is substantially unbalanced, and for the unbalanced component, the changes in the temperature field have very little direct relationship to the changes in the wind field. So that makes it even more complicated to try to interpret the changes in the warm core structure to try to relate them to the changes in the wind. My conclusion of this analysis is that temperature changes are definitely related to the wind changes because the flow is largely balanced. But they're related in a very complex manner that makes it very difficult to actually draw broad conclusions about how changes in this height of the warm core would relate to changes in the intensity or the structure of the wind field. So this brings me to the summary for this lecture. And I guess overall, I think both idealized simulations from my work and then other recent work, as well as recent observations, suggests that there's a substantial degree of variability in the distribution of warming in the eye. However, I think that having a mid-level maximum is fairly common, and having double maximum with a mid-level and a near tropopause maximum are also fairly common. And I think the existence of this double maximum structure is fundamentally, it's related to and a consequence of the basic mean profile of static stability in the tropics. If you look at mean soundings, you tend to have a tropical tropopause layer maximum of static stability, and then a weaker local maximum at mid-levels, and that, I think, is why you tend to get those maximum in the warming. And the budget analyses that I showed indicate that the mean subsidence and the eddy radial advection are both important in warming the eye, and I believe the eddy radial advection, at least in the simulation that I've examined, is particularly important in the early part of the development when the storm is weaker. And then the final part that I was just showing you is that although changes in the temperature and the wind fields are certainly related to each other through thermal wind balance, the relationship is complicated, and it's not a clear connection between the vertical structure of the warm core or intensity change. So any relationships there are actually more subtle to interpret. And while there may be such relationships, it isn't something that comes out clearly from just looking at the temperature field itself. So that's what I have for this lecture. So thank you.
Okay. Thank you. So is there any comment or questions for this topic? You satisfied? All okay. Please.
So the final point, yeah, I understand the point. But you showed just the decaying stage of warm core.
Yeah.
Yeah, the decrease in the wind speed. But how about the increase stage? Increase in wind speed, wind field. Just the same conclusion.
I mean, I
Einstein
think.
stage. How about?
I mean, for this analysis, I only really looked in depth at the changes here because there was a clear, in the simulation, there was a clear change in the height.
Yeah, but wind speed decreased.
Yeah.
Maximum wind speed decreased. The final point.
For this analysis, yeah, the maximum wind speed was decreasing during this period, yes.
But what if?
What if it's increasing?
Yeah.
I mean, I think that the same points hold, that there's the relationship, the gradient wind, although it looks simple at first, is actually much more complicated because it's really everything is, the warm core maximum is like globally integrated perturbation. So that depends on is a function of the gradient, of the radial temperature gradient everywhere, which is related to the vertical shear of the squared gradient wind divided by the radius everywhere. And so I think that makes it such that whatever type of phase of the storm you examine, it's complicated to explain. And there may be cases where you can make arguments for why a certain distribution of temperature change should change the wind structure. But I don't think it'll be easy to do that systematically because and I think the systematic relationships are probably less than one might think, because you can easily have small shifts in some aspect of the distribution that change the height of the warm core maximum, but don't really well relate to the Eyewall wind field, for example. Especially if you have a broad maximum in the temperature profile, you can have a small change in the temperature distribution that's very subtle. And that doesn't necessarily relate to a real systematic change in the Eyewall structure.
In this sense, I think some researchers says the formation of warm core is important for intensification. But your conclusion, that's complicated. So
yeah, I think it's
the formation of warm core
I mean, I
Not
think in some
necessarily.
ways the formation of the warm core is just a consequence of intensification. It's a definition of intensification. If the pressure is lowering, then the warm core must be forming. But yes, some studies have argued that there's some that having warmings at mid levels or maybe at upper levels that somehow becomes a trigger for further intensification. I'm not convinced of that, but I guess it's possible. But yeah, my belief is that it's not. I don't think there's good evidence for the warm core formation as triggering further intensification itself.
Thank you. Okay. Any other question?
With regard to the third point,
Mm-hmm.
the eddy radial advection is important for the mid-level maximum, and mean substance is important for near tropical maximum. Is correct? Or
Yeah, well, I sort of. I would clarify that that both mean vertical advection and eddy radial advection are important for the mid-level maximum. It's not just eddy radial advection. The mean subsidence, especially
yes,
later in the RI period, the period of the strongest warming of the mid-levels, a lot of that is due to subsidence. Earlier, a lot of it is due to eddy radial advection. And then in the near tropopause layer, at all times, it's largely the subsidence.
for the mid-level maximum, which is more important, mean substance or radial advection, eddy radial?
I think it depends. I think it depends on the time that you're looking at. Like the earliest time
Yes.
that I showed, it was almost all eddy radial advection because the mean vertical advection was the wrong sign. So because you were having ascent in the eye.
Yes.
But then later, I think the mean vertical advection was more important. So it's not. Yeah, it looks in here in this simulation. It changes with time which one is more important. They're both important for a lot of the period of RI. And again, I'm not. This is just one simulation, so I think it would be nice to see more simulations to clarify what the role of the eddy radial advection is, to see how systematic this is, whether this is always true in RI or whether this is, maybe it could vary a lot between different storms.
Thank you.
I'm just wondering why the central pressure can be constant while the maximum wind speed will rapidly gain.
Because the pressure wind relationship, there's variation. I think one way of looking at it is that you. So, let's see, if we look at the WRF forecast, the maximum winds decrease from about 110 knots to 90 knots, and the pressure stays about like 938 millibars at both times. If you have an expanding storm, for the same maximum wind speed, a larger storm would, I believe, tend to have a lower minimum pressure. So if you made a storm larger, but the wind speed weakened, it's possible for the pressure to stay, to not decrease that much, or not increase that much, or be nearly constant, like in this case. So the radial profile of tangential wind, or the radial profile of the pressure changes, but because the gradient wind depends on the radius, you can have a lower pressure with a weaker wind when it's at a larger radius.
Maybe the relationship are more clear between the minimum central pressure and the warm core. And
Yes.
maybe the wind and maximum wind speed and the relationship between the warm core might be there are huge uncertainty and complication.
Yeah, I think the relationship is going to be better because the minimum pressure is, if you're in hydrostatic balance, which is a very good approximation, the minimum surface pressure is going to be directly related to the integrated warming above. But it won't be necessarily well related to the vertical structure of that warming, because there are an infinite number of profiles of warming that are consistent with the same pressure. So you could have the warming distributed differently and get the exact same pressure. So that's another reason that it's hard to relate changes in the vertical distribution of the warming to changes in the intensity, even if you're thinking of pressure.
Any others? Okay, so now it's 11:53, so it's time for lunch.
I think so.
Take a group photo.
Yes. So taking group photo and have a lunch until 1 o'clock.
1 o'clock.
Okay. Then we move to part 3 in the afternoon.
Part 6 or something.
What?
You tired? You tired?
Well, I'm tired, but I can do it. Yeah. If you want to hear, if you're not bored by it, yeah.
It's an energy here.
So that is okay. I think we can resume the dance talk from 1 o'clock about that until 2 o'clock around.
Okay.
Okay, so time to group photo.
Okay. Anyway, thank you very much. Have a group photo